Okay, a point of inflection is the point where the graph turns from concave up to concave down. The point of inflection is where the graph changes from concave down to concave up. The point of inflection is where the graph turns from concave up to concave down. So this is our point of inflection. I'm going to call it POI. POI. That's our point of inflection. And we're going to find that point of inflection. It's an ordered pair, and it's where the graph changes concavity. So where the graph changes concavity. Okay, let's discuss the concavity and find the points of inflection for f of x equals x to the fourth plus x cubed minus 3x squared plus 1. Now I know that the first two problems that we did, the example and the try, that it's really hard to, surpass how much fun those were finding the second derivative, but I'm going to give it a try. This is a polynomial function. Let's see if this one is even better than the first or the second. It's actually going to be a lot better because finding the second derivative of a polynomial function, much less intense. Let's just put it that way. So our first derivative is 4x cubed plus 3x squared minus 6x. We need to get to the second derivative to talk about the concavity. So the second derivative is going to be 12x squared plus 6x minus 6. And from here, I can factor out a 6. I'm going to try and factor this further. So that's going to be 6 times, let's see, 2x x. We know it's going to be a 1 and a 1. We need a positive and a negative. I think that's it. I think that is it. I'm going to move this over here. And I'm going to say my x values are 1/2 and -1. Now, in a polynomial function, we don't have any values that are undefined for x that in the original in the second derivative in this case, because that second derivative is a quadratic. So we don't, no undefines. I'm just going to put no undefines. I like to make sure that I'm continually addressing that so I don't forget to address it on a problem in which it does make a difference. Okay, the domain for this original function is -infinity to +infinity, and then I have, excuse me, but -1 is to the left of 1/2. So -1 and then +1/2 are my numbers that are going to break up my domain for my concavity of the graph. So we're going to test for concavity into the second derivative. So we're going to go into that second derivative, and I'm going to put in maybe a -10. When I put a -10 in, I'm going to get a negative times a negative, which is a positive. So a negative times a negative is a positive. And when I put a 0 in, 0 is between -1 and 1/2. When I put a 0 in, I'm going to get a negative times a positive, which is a negative. And if I put a +5 in, I'm going to get a positive times a positive, which is a positive. So our concavity, we've got concave up from negative infinity to negative 1, and then again from 1/2 to infinity. And our concavity is going to change. It's going to go to concave down from negative 1 to 1/2. So where that concavity changes, that's an x value, okay? This is an x value. So our point of inflection, we've got two of them. We've got 2 points of inflection. We've got one that has an x value of negative 1, and the other one that has an x value of 1/2. So we've got 2 of these. These are ordered pairs. Unlike the pink intervals, those are intervals, right? Negative infinity, negative 1, that's an interval of an infinite set of numbers. 1/2 to infinity, an infinite set of numbers. Negative 1 to 1/2, an infinite set of numbers in between. But our point of inflection is literally an ordered pair. It's an x, y, an x, y. It's ordered pairs that are on the original graph f of x. So f of negative 1, when I put a negative 1 into the original function, I am going to get 1 minus 1 is 0, minus 3 plus 1, negative 2. And when I put a 1/2 in, 1/2. Okay, I don't want to cheat. I've got it written down already, but I'm not going to cheat. 1 over 2 to the 4th is 16. And then I've got 1 over 8, so I'm going to need another 2 there so I can get a common denominator, right? And then negative 3, negative 3 over 1/4, right? Or times 1/4, so that's negative 3/4. And then and I'm going to need a 4 there. And then plus 1, that's 16 over 16. So 1 plus 2 is 3, 3 minus 12. 3 minus 12 is negative 9. Negative 9 plus 16 is 7. Hot dog, 7 over 16. I looked at my answer key, and that is correct. Sometimes I just amaze myself with how well I can add and subtract. You should be amazed too. Maybe not with yourself, but you should definitely be amazed that I can add and subtract properly at times. Excellent, excellent. Okay, so now we've got find the relative extrema using the second derivative test. Okay, this was a lot to kind of chew right here, this points of inflection. It does just continue the concavity, but I want to take some time with this relative extrema using that second derivative test. So I'm going to pause right now so I can stop and I can literally take a break, think about the words that I want to use, and then I'm going to come back in the next video and I'm going to explain to you relative extrema using the second derivative test. I will be honest with you. It's not something I do all the time. I usually will just go through the first derivative test like we did in the first 2 sections of this chapter, and then I will use the second derivative to actually find the concavity and points of inflection. There are times though where going right to the second derivative can save you a few moments, a few minutes. It can give you some extra time that you wouldn't otherwise have if you were going through all of the motions that we normally go through.